Welcome to Savi YouTube channel created by Sai Vidya Institute of Technology, Bangalore. In the last session, we have started a new theorem, that is maximum power transfer theorem. We have considered the case 1, DC source with purely resistive load. So, we have considered the DC source and pure resistive load, and it is a variable load, and derived the condition for maximum power transfer, and we got a condition for maximum power transfer for this case is RL should be equal to RS, means when the value of load resistance is equal to the value of source resistance, maximum power can be transferred to this load when the source is DC and the resistive load is considered. So, now we are going for second case. Second case, I will change the source to AC, keeping the load same. Now, let us derive the condition for maximum power transfer. So, case 2, I will change the source to AC source with purely resistive load, and it is again a variable load. When I consider AC source, so source impedance I will consider complex. I am going to consider the source impedance complex. Now, how to represent AC source? Just write AC symbol, and since it is AC source, I am going to consider the impedance here for source. Impedance is ZS, and it is complex, therefore I write RS plus JXS, RS plus JXS, and the resistive load is same and it is a variable load. Let us now derive the condition for maximum power transfer for this case. First, what I should do, since I want to get the equation for power, to find the power, I should find the current. So, from the circuit, I is equal to what? Vs divided by Zs plus RL. Okay. So, that is equal to Vs divided by what is Zs? Rs plus JXS plus RL. Therefore, I is equal to Vs divided by Rs plus RL, Rs plus RL plus JXS. So, whenever we are finding current in the case of AC, or if you are finding the power, we should find the magnitude of current. To find the power, we should find the magnitude of current. Now, let us find the magnitude of current here, that is equal to Vs divided by root of Rs plus RL whole square plus X square. This is the magnitude of current. Now, I have to get the equation for power. Next, power transferred to the load. Power transferred to the load, P is equal to magnitude of current square into the load resistance RL. So, that is equal to current equation. Let us substitute here, Vs divided by root of RL plus Rs whole square plus X square. This is whole square into RL. That is equal to Vs square divided by root, and this get cancelled, and we get Rs plus RL whole square plus X square into RL. Let this equation number 1. So, this is the equation for power transferred to the load. but my intention is to find the maximum power transfer. We just got the power equation, but my intention is to find or get the condition for maximum power transfer. Then what I should do? Then I have to differentiate this equation with respect to the variable, that is RL, and then I have to equate to 0. Then to get the condition for P max, to get the condition for P max, differentiate equation 1 with respect to RL and equate to 0, that is dP by dRL must be 0 is the condition for maximum power transfer. Now let us differentiate this equation with respect to the variable RL and then equate to 0 using quotient rule, that is since it is U by V form, let us use quotient rule to differentiate this equation. Let us differentiate using quotient rule. So dP by dRL is equal to, let us use quotient rule. So U by V form, denominator square, that is denominator square, RS plus RL whole square plus x square, this is whole square, denominator square, then keep the denominator, that is this one, that is RS plus RL whole square plus x square, then differentiation of dash represent differentiation of numerator. So since V square is constant, take outside, it is constant. Now differentiation of numerator is 1. This is V square, take it outside because it is constant. Now only you have to differentiate this. Differentiation of RL is 1. With respect to RL you are differentiating minus, keep minus. Then U, keep the numerator and differentiation of denominator. What is the differentiation of denominator with respect to RL? So this is given by, this is 0, this so 2 into RS plus RL is equal to 0. Okay. Now differentiation of denominator with respect to RL. So 2 into RS plus RL, this is 0. Okay. So this is what you are getting. Now let us, if you cross multiply, what happens? We get V square into RS plus RL whole square plus x square minus 2RL into RS plus RL is equal to 0. Now we want the value of RL. Therefore, if you take this this divided by V square is equal to 0. That's why you can rewrite like this: RS plus RL whole square plus x square minus 2 RL into RS minus 2 RL square is equal to 0. Now I'll apply here A plus B whole square formula, that is RS square plus RL square plus x square minus 2 RL RS minus 2 RL square is equal to 0. Now here I am missing one term, A square plus B square plus here I am missing one term, RL square plus 2RS RL. Okay. Now this get cancelled. We get here RS square plus RL square plus x square minus 2RL square is equal to 0. Next step, RS square. So 2RL square minus RL square. is minus RL square plus XS square is equal to 0. So, RS square plus XS square is equal to RL square. So, I want RL here, therefore, I can write RL is equal to root of RS square plus XS square. That means the value of load resistance must be equal to this value to get the maximum power transfer to the load. Now, always we are going to find the value of load resistance. What would be the value of load resistance for maximum power transfer? Because we are considering this as a variable load. So, what value we should adjust to get the maximum power? That is what we are doing here. Now, I will express this in the other form. Since we know that source impedance, what is source impedance? ZS is equal to RS plus JXS. RS plus JXS. Suppose if I take the magnitude is equal to what? Root of RS square plus XS square. That means this is same as this. Therefore, I can rewrite this as RL should be equal to magnitude of ZS. Magnitude of ZS. So, this is the condition for maximum power transfer in this case. That means when the source is AC, source impedance is complex and the load is purely resistive with variable, the condition for maximum power transfer is the load resistance value should be equal to magnitude of source impedance. So, this is the source impedance. So, we should take the magnitude of this value and we have to adjust the load value to this, the magnitude of this source impedance, to get the maximum power transfer in this case. Now, suppose if ZS value is equal to 2 plus J4, assume that this is the value of source impedance. Then what is the magnitude of this? So, magnitude, suppose if ZS is equal to 2 plus J4, its magnitude is given by 2 square plus 4 square under root, that is equal to 4 plus 16, that is equal to root of 20. So, what is root of 20? It is around 4.7 say 5 ohms, 4.75 ohms. That means if the source impedance is 2 plus J4, then to get the condition for maximum power transfer, RL should be equal to magnitude of ZS. So, what is the magnitude of ZS you are getting? 4.75 ohms. So, it is 4.75 ohms. That means if you adjust the value of load resistance to 4.75 ohms, then maximum power can be transferred to this load. That is the conclusion from this discussion. And how you can state the theorem in this case? So, in a linear bilateral network consisting of AC source with purely resistive load, maximum power can be transferred to this load when the value of load resistance is equal to magnitude of source impedance. Okay? This is how you can state the statement of this theorem for AC source with purely resistive load. Now, let us go for case 3. I will go for case 3. I will keep the source same and source impedance is also same. Now, I will change the load to complex load. Complex load means again I will take a load impedance as ZL is equal to RL plus JXL with both RL and XL are variable. Okay? Now, let us go for case 3. Case 3, I am considering AC source. Source impedance is complex and load impedance is also complex. So, that is represented as RL plus JXL. I am considering both RL and XL are variable. Both are variable. You can take the case like this with only RL variable, keep XL constant, XL variable, RL constant. Like that also you can consider. but I am considering directly with both variable. Okay. Now, the procedure of deriving or getting the condition for maximum power transfer remains same as that of earlier two cases. Now, what I should do? First, I should find the current. Then, I should find the magnitude of current because I want to find the power. Then, get the equation for power transfer to the load. Once you get the equation for power transfer to the load, then to get the condition for maximum power transfer, you have to differentiate that power equation with respect to the variable. So, we are considering here two variables. Let us see how to get the condition first. So, from the circuit, get the equation for current is equal to Vs. So, I is equal to V by sum of the impedance, that is Zs plus Zl, that is equal to Vs divided by Zs, that is Rs plus Jxs plus RL plus Jxl. Now, group real and imaginary terms. So, I is equal to Vs divided by Rs plus RL plus J Xs plus XL. Okay. Now, what I should get? I should get the magnitude of current because I am finding the power. So, magnitude of current is equal to what? Vs divided by, so Rs plus RL whole square plus Xs plus XL whole square under root. This is the magnitude of current. Next, I should get the power equation. So, power transferred to the load, P is equal to magnitude of current square into RL. Very, very important. Though you are represented the load as ZL, you should not write ZL. ZL is equal to RL plus JXL. Why I am considering only RL here? Because power is always dissipated in the resistive part of the load. Power consumed by a pure inductor is 0. The power consumed by pure capacitor is also 0. Power will be consumed by only the resistive part of the circuit. Hence, we must write power equation here I squared into RL only. Next, let us substitute here I is equal to, so Vs divided by, so Rs plus RL whole square plus Xs plus XL whole square. So, if you square this, root and this get cancelled. Okay. Numerator becomes what? It becomes square into what? RL. This is what? Our equation. Root and square get cancelled. Okay. So, this becomes square. Write RL as it is. So, this is the power equation. Now, what I should do to get the condition for P max? To get the condition for P max, what I should do? I have to differentiate this equation with respect to the variable, and then we have to equal to 0. So, that is dP by dRL should be 0. But since we have two variables, what is the procedure we are going to follow is, first we are going to differentiate this power equation with respect to XL, keeping RL constant, and then equate to 0, then you will get one condition. First, what you should do? Differentiate this power equation with respect to XL, keeping RL constant, then get one condition. Then substitute that condition in the power equation, get new equation. That new equation again you differentiate with respect to RL, keeping XL constant. Then look at another condition. Both the conditions are used to get the final condition of maximum power transfer. So, this is the procedure we are going to use. Just observe here, definitely we will understand. So, to get the condition for maximum power transfer, we have to differentiate this equation first with respect to XL, keeping RL constant. Later, differentiate the power equation with respect to RL, keeping XL constant. That is what we are going to do. Now, let us follow this procedure now. Now, this power equation I have rewritten here for my convenience. Now, let us derive the condition for maximum power transfer. First, what I will do, I will assume RL to be constant, XL to be variable. First, assume RL to be constant and XL to be variable. Then differentiate this power equation with respect to the variable, that is XL, and then equal to 0. Okay. So, dP by dXL is equal to anyhow this is constant. Again I will make use of quotient rule. So, denominator square, that is RS plus RL whole square plus XS plus XL whole square. Next, keep this RS plus RL whole square plus XS plus XL whole square. That is, you are keeping the denominator as it is. Now, differentiation of numerator. What is the differentiation of numerator? Since you are differentiating with respect to XL, the differentiation of RL becomes 0 because no XL term. 0 minus keep the numerator as it is. Then differentiation of denominator. What is the differentiation of denominator? First term is 0. This becomes 2 times XS plus XL. 2 times XS plus XL. Okay. This is what is equal to 0. This is equal to 0. I think this is just a quotient rule. We are using this denominator square. Then here keep the denominator. Then differentiation of numerator is 0 minus keep the numerator as it is. Then differentiation of denominator. You might be knowing the quotient rule very well. Now, if you cross multiply, this becomes 0 and you have this is constant. So, if I consider only the numerator, again this becomes 0. Means anyhow this, since you are multiplying here, this first term is 0, then what happens here? We will get only this term, that is minus 2RL into XS plus XL is equal to 0. This term is 0. Cross multiplying, this whole term becomes 0. Only remaining with this term. So, what I want? Always I want the value of load impedance in terms of source impedance. That is why here XS plus XL can be written as 0 because 0 by anything is 0. Now, I want XL. What is XL now? XL equal to minus XS. XL is equal to minus XS is one condition, one of the conditions when you consider RL constant, XL variable. Now, what I should do? I have to substitute this condition in this power equation and you will get a new equation of power. That new equation of power, now you have to differentiate with respect to RL, assuming XL to be constant. That is the procedure. Now, substitute this value in equation 1. This is your equation 1. Then, if you substitute here XL equal to minus XS, what happens? This becomes 0. Then, what is the new power equation? Then new power equation is given by P is equal to Vs squared into RL divided by Rs plus RL whole square. Rs plus RL whole square. Now this is your new power equation because the second term becomes 0. This new power equation, now I have to differentiate with respect to RL, assuming RL to be variable. Okay. Now what I have to do? All of you observe here. Now differentiate equation 2 with respect to RL, assuming XL to be constant. Okay, assuming XL to be constant, that is dP by dRL must be 0 now. dRL must be 0. This is the condition. Now let us differentiate this equation. That is the second equation. Now I have to differentiate. So let us use quotient rule. That is dP by dRL is equal to so denominator square, that is Rs plus RL whole square, denominator square, then keep the denominator here, that is U, that is Rs plus RL into this differentiation of numerator is 1 because Vs is a source which cannot be 0 and it is a constant. Actually you have to take it outside. Vs square should be outside. Next, keep minus, keep the numerator as it is, then differentiation of denominator is given by 2 times Rs plus RL. Okay, so this should be equal to what? 0. Here Vs is a source that has to supply power to the load, hence Vs cannot be 0 and it is a constant, so take outside here. So that means then you are considering only these terms to differentiate. So denominator square and keep this denominator here, then differentiation of numerator is 1 minus, keep the numerator as it is, then differentiation of denominator 2 Rs plus R. Then if you cross multiply this becomes 0. Anyhow this is, if you rewrite that also becomes 0. Therefore what is remaining now? Rs plus RL minus 2 RL into Rs plus RL is equal to 0. This is 0 and if I take this, 0 divided by this is equal to 0. Okay. Let us simplify here. Rs plus RL minus 2 RL into Rs plus, this is square now, this is square, sorry, this is square, minus 2 RL square is equal to 0. Let us simplify this. A square plus b square plus 2ab minus 2RL into Rs minus 2RL square is equal to 0. Okay. Then this I can cancel. Then what happens here? So Rs square minus 2RL square plus RL square is minus RL square is equal to 0. Therefore Rs square is equal to RL square or nothing but RL equal to Rs. Actually already we derived this condition in the first case, just once again I did. That means now you are getting two conditions here. First condition you got XL equal to minus XS. This is one condition we got earlier. Now we are getting this condition. So both the conditions are used to get the final condition of maximum power transfer. Now, so when the source is AC, load is complex, the condition for maximum power transfer is the RL must be equal to RS here. RL value must be equal to RS. And XL value must be equal to what? Minus XS. This XL value must be equal to minus XS. Now let us rewrite that condition in a proper way for our convenience. Okay? We know that what is the load impedance? So load impedance ZL is equal to RL plus J XL. So condition for maximum power transfer is what? So RL should be equal to RS. RL should be equal to RS and XL should be equal to minus XS. Then what happens? Then ZL becomes equal to, I am going to replace RL by RS, okay, XL by minus XS, that becomes minus JXS. So, what does it mean? Our source impedance is RS plus JXS, but we have to replace the load impedance by RS minus JXS. Therefore, I can write this as complex conjugate of source impedance. Source impedance is RS plus JXS. We want RS minus JXS. Therefore, we have to take the conjugate of this. That's why I'll write here ZL should be equal to ZS conjugate. So, this represents complex conjugate. Complex conjugate of ZS. Okay. This is the condition for maximum power transfer. Now, so when the source is AC, source impedance is complex and load impedance is also complex, and if both RL and XL are variable, the condition for maximum power transfer is the value of load impedance must be equal to complex conjugate of source impedance. So, what is the statement of the theorem? You can say, if I suppose the question is asked, state and true maximum power transfer theorem for AC circuits, then what is the statement you can say? In any linear bilateral network consisting of AC source with complex load, with both RL and XL are variable, then maximum power can be transferred to the load if the value of load impedance is equal to the complex conjugate of source impedance. This way you can state the theorem. Then you can prove this theorem. Now, in this maximum power transfer theorem, in these two sessions, we considered three cases. So, first case, DC source and with the pure resistive load. Second case, AC source and the load is pure resistive load. Case 3, AC source with complex load. Now, let us form a small table to conclude this discussion. So, conclusion from these two sessions, we have considered three cases. So, first case, case 1, source we have considered DC source and the source resistance we have considered here. We have taken the load as purely resistive load. Then the condition for maximum power transfer is the load value should be equal to the source resistance value, that is RL should be equal to RS. Case 2, I have changed the source to AC like this, and I have changed the complex load, that is complex impedance, but the load is same. That means I have changed the source, AC source, in this case keeping the load same. Then what is the condition for maximum power transfer? This value of RL should be equal to magnitude of this source impedance, that is second case. Case 3, Keeping the AC source same, have changed the load to complex. Then the condition for maximum power transfer is ZL must be equal to ZS conjugate, that is case 3. The value of load impedance should be equal to complex conjugate of source impedance. Okay. So, these conditions we are going to apply to solve the problems on maximum power transfer theorem. So, if you want to solve problems on maximum power transfer theorem, just you must know Thevenin's theorem, because the given network you are going to convert it into a Thevenin's equivalent circuit, that is a voltage source in series with a resistance or impedance. Then we are going to find the condition for maximum power transfer and also the maximum power transfer to the load just by using these conditions. That's all. Thank you very much.